Welcome to week 8 live session of molecular spectroscopy, a physical chemist perspective. I am Arko Prabhu Chaudhary. I am a PMRF at the Department of Chemistry, IIT Bombay. I am a teaching assistant in this course. I am helping you to solve numerical problems from outside, uh, means the means from the questions that I am gathering from different books as well as from the assignment problems. And today our goal is to study the symmetry part. Symmetry, what a symmetry operation, what is symmetry, and how symmetry and group theory is going to help us in um, this molecular spectroscopy course. So why we are actually reading the symmetry portion? Because um, we till now what we have discussed in this course is basically about the diatomic molecules, the vibrations, Raman effect, and all what we have understood on the basis of diatomic molecules. Now, actually, to understand or to simplify the problems in the polyatomic molecules, we want symmetry. It will simplify our problems. So Professor Datta has already taught this part, and I am recapitulating these portions. So let us start with what is a symmetry element and what are symmetry operations. So symmetry operations is a what we are doing, means what we can do to on a material or on a molecule to get an equivalent position or equivalent structure. So that is what is a symmetry operation, and the tools we are going to use for a symmetry operation is symmetry elements. So like symmetry elements, all know identity, right? Or E. This means almost means we are doing nothing. It's like a idle system. So if we use this identity or use this symmetry element on to so this symmetry element or use this symmetry element as an operation, then we are going to get back our uh, molecule or whatever structure we are working on. Similarly, there can be rotation. There is some problem. So this glitch has happened earlier also. I'm very sorry for that. So for rotation like Cn, where n is 360 degree by theta. So by what angle you are rotating? That rotation could be on a axis, and even reflection from a plane, and another could be point of inversion, that is I. Okay. Now what we want to know is how. So there, so symmetry operations are, we will use these elements functioning on our molecules, so that will be a symmetry operation. Equivalent structure, or whatever you can say, position. Okay. Now there is something called basis. Okay, that is on which symmetry operations will be performed. And when we perform this symmetry operation on these basis, we would be able to generate or write transformation matrix. From there, to generate transformation matrix, matrices or matrix. Okay. And before going there, let me once check if the Google Meet is fine. Oh my God, I didn't want to leave. Rejoin. Very sorry for this delay. Let me get back to the discussion we are doing. So, suppose you have a molecule like water, H2O. It has symmetry element, like, let me draw it for you. H. Okay. So obviously it have identity element E. It have a rotation along this principal axis, that is Z. We can say if this H2 molecule is on a plane of this uh, display, then this Z is actually coming out of the display. Sorry, this is along the display board. Okay, this Z. So actually along Z there is an C2 symmetry, C2Z. Okay, and there are two planes. One plane is along the molecular plane, which is along the display. That is, suppose I can say this is Y and this axis is X. Then the molecular plane is XZ, which is sigma V XZ, and there is another plane, that is sigma V dash YZ. Okay, so these are the symmetry elements, and it forms actually a point group C2V. Okay, why I have written this as sigma V and this as sigma V dash? Because actually both are vertical symmetry planes elements, but and one thing to observe, that these vertical planes will always uh, it will always have this z axis in it, or you can say this rotational symmetry element will be on these planes. That is one thing. That is why these are called vertical planes. There are other planes also, like molecular plane, sorry, dihedral planes and all. So that will not that will be perpendicular to your uh, the dihedral plane will be perpendicular to your principal axis of rotation. So here it is called C2 because uh, we if we rotate it by 180 degree, that is 360 by n. How to determine the n? N is 360 by theta. So if right now we are rotating it by 180 degree, that's mean it is a C2 symmetric and we are going to get an equivalent structure. Okay. So similarly with sigma v xz and sigma v dash yz, we are going to get these molecule bags. That is why upon these symmetry operations, we are going to get an equivalent water molecule. So that is, so these are called symmetry elements and symmetry operations, right? Now we want to get the transformation, and as they are similar but uh, lead to different, uh, like how I will tell you, suppose this is HA and HB. Now if you use the plane sigma v dash yz, then actually your HA will become HB. This position will change, interchange A and B. And if you use a sigma v dash xz, sorry, sigma v xz and the molecular plane, then your hydrogen atoms nothing actually interchange, or the positions remain the same. So actually, even though all the result is equivalent, but they have a different kind of uh, operation. That's why these are uh, non-equivalent symmetry elements, or this belongs to different class. Okay. Now based on this symmetry operation, uh, we will get different kind of uh, representation. Obviously I told you how. So this representation is actually will be, so for each symmetry operation, we can get symmetry for can get a transformation matrix, and how it will look like. Suppose um, we are taking the basis as xyz coordinates, xyz coordinate, and if I am applying identity operation E, then actually I am going back xyz coordinates, right? There is no change on this, whatever there in this oxygen atom, right? So actually your E can be represented in a matrix 1 0 0 0 1 0 0 0 1, right? So this is a transformation matrix for E. What would be the transformation matrix for C2Z? If we apply C2Z on XYZ, then what we are going to get? X, if we rotate it by 180 degree, X will become minus X, right? Y will become minus Y, Z will remain unchanged. So here your C2G Z is actually minus 1 0 0 0 minus 1 0 0 0 1. Similarly, you can get a transformation matrix for sigma V xz working on xyz. You will see that your x xz plane, so this is the molecular plane, so x and z remain same, and y will only have minus y. So x will remain unchanged, y will be minus y, and z will also remain unchanged. So your actually sigma v xz is The transformational matrix is 1 0 0 0 minus 1 0 0 0 1. Okay, and what about sigma v yz, sigma v z dash? That is actually going to give you, so I'll directly write the transformational matrix. As you can see that your for yz only x is going to take change place, and z and y will be remain same. It will be minus 0 0 1 0 1 0 0 0 minus 1. Okay, so on the next page I will just write for C2b what we have got. C2b point group, when we the basis set, basis is Cartesian coordinate x y z, then we got transformational matrix for E 1 0 0 0 1 0 0 0 1. Okay, for C2z we got, for C2z we got minus 1 0 0 0 minus 1 0 0 0 1. For sigma v xz we got 1 0 0 0 minus 1 0 0 0 1. And what about sigma v dash yz? Minus 1 0 0 0 1 0 0 0 1. Okay, somebody joined the meeting, I think. Yes. Okay. So from here, from this transformational matrices, actually we can generate what we know as representation. But to get, so what is a representation? I will write it here. Collection of all these matrices. Transformational matrices. Okay, of a particular basis. Now from here, actually you can see I will use maybe a different color pen. So we can actually block factorize this thing into, these are, if you see these particularly for C2b, what we have obtained is actually the transformational matrices with only diagonal elements. So so this is not going to happen all the time, so this is a special case. So, and if we are only getting the diagonal element, and if you can also see the non-diagonal elements are 0, so you can easily block factorize them into smaller matrix, or you can say these are your um, you can say that how your basis is actually going to behave when these symmetry operations are going to be performed. So what I mean by that, I will write it here. So this is actually, if I block factorize it, I'll erase the non-zero part. I'll write it like this. For here I am getting minus 1, minus 1, 1. Here I am getting 1, minus 1, 1. Here I am getting minus 1, 1. and the basis set was x, y, z. So we can see for when we are operating with the identity operation, the x is symmetric with x is going to be symmetric with respect to the identity operation, but with respect to the C to Z it is going to be antisymmetric. And similarly for sigma v symmetry operation, x is going to be symmetric, and for sigma v dash it is going to be antisymmetric. But so this gives us an idea what a representation is. So this is a representation of this of a particular basis set. Now here we have taken only the Cartesian coordinates as our basis set. So we can take anything, right? For a H2O molecule, we can take the atoms uh, H1, H2, and oxygen, right? There are two hydrogen and two oxygen. Even what we can do, we can take the p orbitals of the oxygen, or maybe the 1s orbital of the hydrogen, like in a various manner, or in a very, so we can take anything as basis set. But the problem is, the beauty of this thing is we are going to get a specific set of representation, and these representations could be defined into two things. One is irreducible representation, where it can't the representation with dimensionality 1 are always going to be irreducible, and but that is not a definition, because the irreducible representation can have your dimensionality more than 1. But the thing is, what I am trying to say, that you can't break irreducible representation into a sum of or linear combination of different irreducible representation. But another form is reducible representation, where you can break a reducible representation into a sum of or you can present that in a linear combination of irreducible representation. So when you are actually going to take your basis as what I was saying, suppose now instead of Cartesian coordinate, you are going to take your O, H1 and H2 for oxygen, right? H1, O, H. So this is your C2Z, right? So now what you are going to expect for E, C2Z, sigma V X Z, sigma V dash YZ. So what you are going to see for, so the your transformational matrix will be 3 into 3, but let us see what we are going to see. For identity, obviously all will be same, right? Right. Now for C2Z, your oxygen is going to remain same 100, but your H1 and H2 are going to interchange their position, right? H1 will going to be your H2 and H2 will be your H1, so it would be 0 0 1 and 0 1 0. Okay. Sigma v xz, xz is x is this direction, y is this direction. So your xz is a molecular plane, so all will be, there will be no change. Actually there is going to be change, the hemisphere are going to change the place, but uh, the position is, the position of the atoms are not going to be changed, right? So it will be 1 0 0 0 1 0 0 0 1. So no atom has displaced. What about uh, sigma v dash yz? For yz, it is going to be again your oxygen is going to remain same 0, 0, 1, 0, 0, and these are going to interchange their place. Even though C2Z and sigma V dash YZ have a similar or same look-alike transformational matrix, but it still, if you see, in case of uh, C2Z, the hemispheres are going to be changed, but for C2 sigma V dash, the hemisphere of the spherical orbitals or atoms are not going to be changed. So from here, we can't really block factorize into, so here are there are non-zero diagonal element. That means that your there is an interchange between the bases upon the symmetry operation. That is what it actually means. So the best possible way to block factorize will be to do this. And you have to use the same block for all your transformation matrices for a particular basis set. So from here, what you are actually getting, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1. This is your oxygen. And your X, Y actually transform together. That is why we can't really block factorize them into even smaller representations or transformational matrices. So these 1, 1, 1, 1, these are actually known as your totally symmetric uh, representation. But here the question comes, main question, that if we are taking, so the one thing we understand here, that a representation will depend on the basis, right? What basis set we are using, then obviously different representation or different basis set. So the main question will be, how would we know oh, how do we know the number of irreducible representation? Possible. And another important question, which representation is reducible and which one is irreducible. So these are the question we have at this point of time. Okay, so now so to solve this problem, actually we are not going deep into the symmetry or the group theory, but in our disposal we already have one, you can say, arsenal, that is the great orthogonality theorem. So this theorem will help us to actually understand what is the relationship between the uh, reducible and irreducible representation. This actually simplifies it. So I'll first write down the mathematical expression for this. Summation over R. R means the symmetry operation. Gamma I R Mn. So this means this is what gamma I R Mn is Mn Mnth element of the transformation matrix of symmetry operation R in the ith irreducible representation. So let me write down the full expression. Then it comes gamma j m dash n dash complex conjugate of this element is going to be H, order of the point group, by Li into Lj, where Li, Lj are dimensionalities of ith and jth irreducible representation, and then there is delta Ij, delta Mn, and delta M dash. Delta n dash. So these are conical delta, where when I equals to j, it is going to give you 1. When I not equals to j, then it is going to 0. Same for if it is m equals to m dash, then it will be 1, else it will be 0, like that. So I told you what is a gamma I R Mn means. So this is an mnth element of a transformational matrix, where m is the number of row and n is the number of column. So we are pointing out a particular element of a transformational matrix of a symmetry operation R in the ith reducible matrix. If we multiply it with another element of the same symmetry operation from a same or different irreducible representation, we are going to get something that is going to given by this great orthogonality theorem, where I will also point out what Li and Lj are. These are dimensionality of ith and jth irreducible representation. Okay, and H is order of the point group, which is basically nothing but total number of symmetry operation. Now, using this great orthogonality theorem, we have 5 working rule in our hand. Some working rules. The first one being the character, sorry, I will not use this as a first one. The first one would be, if I am, so number of, so the first question we are going to answer, we had 2 questions, right? So the first question, first answer would be number of irreducible representation is going to be equal to the number of classes of that particular point group. Suppose we are dealing with a C2V point group, then the number of irreducible representation will be going to be 4, because there are 4 classes in C2V point group. Okay. Now the next working rule will be that the character of the symmetry operation E is always going to give you the dimensionality of that particular irreducible representation. Okay. Now the third one would be, if you take a square of these dimensionalities along different, along your number of irreducible representation, you are going to get your order of that point group. So what I'm trying to say is, if you take a, if you are going to sum over I Li square, so which means nothing but you are going to get chi I E, character of E, and take a square of that, you are going to get total number of symmetry operations of that particular point group. So right now I am writing these working rules, and when we are going to first observe a character table or for a point, for a particular point group, we will discuss that what are this. Okay, so first let us write these rules. And now comes one of the important rule. As you can see, this deals with the orthonormality of two matrix elements. So the another rule would be, So I will try to prove one or two of these working rules, which was not done by Professor Datta due to the time permit. But there is not much time on this course. So I will try to derive one or two of these working rules, which are there obviously in F.A. Cotton's book, which is a very famous book for symmetry and group theory. You can always go there and go through that book for the symmetry part. Okay. Now the fourth working rule is related to the um, uh, orthogonality of these elements. First, I will talk about the normalization. So these are actually rules as great orthogonality theorem, but it deals with orthonormality. So both orthogonality and normalization is a factor here. So the one of that will be if you sum over the symmetry operations, you are going to see that your character of the character of ith irreducible representation of a particular symmetry operation, if you take a square of that, again you are going to get H, order of the matrix or order of the point group or the total number of symmetry operation. So this is little different than the previous one. Previous one was sum over I, means it was along the irreducible representation, you are summing over that, and now for a particular irreducible representation, you are summing over all the symmetry E operations. And the orthogonality rule is that when you do the same, sum over the operation of a particular irreducible representation, suppose you are going to take character of ith irreducible representation and multiply with the character of the same operation but from jth irreducible representation, you are going to get 0. Why? Because now see your I and j, your I not equals to j, then delta ij is going to be 0. That is what this orthogonality rule is about. So this is easier to visualize. I will tell you how you are going to get from these matrix elements to this character. That I will maybe I can solve it. I can show it to you right now. Okay. Okay, I will do that. Maybe this proof will help you to understand what I am trying to say. The working rule 3, a working rule 4 and working rule 5. So suppose I'll write the rule again, the great orthogonality principle or theorem, sum over R gamma I R mn multiplied by gamma j R m dash n dash, obviously a complex conjugate of that. When you multiply that, you are going to get H divided by square of Li into Lj delta m m dash delta n n dash, sorry about that, delta n n dash and delta ij, obviously it is there. Now suppose we are going to deal with the same irreducible representation, then your I equals to j, right? And it will give you delta ij is going to be 1. Good. And we are also going to means fix that your n is going to be m, means we are only going to deal with the we are trying. So what is this gamma I rmn? What I already discussed, this is an mnth element of a transformation matrix of symmetry operation R in a ith irreducible matrix, a irreducible representation. Now we have already fixed that we are going to deal with the same irreducible representation. That is why your I and j are equal. Now I am going to take only the diagonal elements. And in case of diagonal elements, what is going to happen? Your m is going to same as n. So that is what I am trying to say. That n equals to m and n dash equals to m dash. For this particular case, what we are going to get? We are going to get sum over r gamma I r mm multiplied by, and we are also taking the into care that these all are real numbers. There is no imaginary terms. Then the complex conjugate is going to be the same. Then gamma jth r m dash is going to be equals to h root over. Now li equals to will be lj, so both are li. Now delta m dash delta n, so both will be delta m dash, right? Because we have defined n equals to m and n dash equals to m dash, and obviously delta ij is already 1. Now you see what is a delta m dash. This is going to be 1 when m is equals to m dash, right? It will be 0 else when m not equals to m dash. And what is the square? What is going to be the square of delta m dash then? It will be 1 when m equals to m dash and 0 else, right? So actually delta m dash square is also delta m dash, what I am trying to say. So instead of 2, I am going to write it. So I am not going to jump steps. So this may take some time, but it will help you to understand maybe. Acha, I have made one mistake, then I am taking again I and j. So both are same. I told you that I am going to take it from the same representation, irreducible representation, then both are I. Okay. And it become Li and delta m dash. Okay. Now if we sum over all the m and m dash possible, okay, then now again sum over all the m and m dash, what we are going to get? We are going to get what I told you, that sum over m, sum over m dash. So what will be the possible values of m? We are going to see that what we are going to get. So this is r gamma I r mm multiplied by gamma I r m dash sorry, is equals to sum over m, sum over m dash, h by li, and delta m m dash. So if I take m and m dash inside, in the left hand side we are going to see sum over I. First I will take only m for this gamma I r mm, and sum over m dash or gamma I r m dash, because sum over a, so this part is constant with respect to this sum, a sum over of this, because and means they are both independent. That's why we can take them into a product of two functions. And if you see h by li is independent of this sum, it will come out m dash and delta m dash. Okay. Now see, we know what is this. This is mth element of a transformational matrix of a symmetry operation R, right? And we have defined it that m equals to m means we are taking only the diagonal elements. So now, did I cover that? But if you remember that, if you, for a transformational matrix, like if I go back here, so for a transformational matrix, if you take the sum of the diagonal parts, you are going to get the character of that matrix. So let me at least introduce here a character of the symmetry operation is known as chi, that is sum of the diagonal elements of the transformational matrix. Obviously it's for a specific basis set. Now here, see, so we are only dealing with the diagonal element, and for all the diagonal elements, suppose earlier it was 1, and for sum over m you are going to get sum over r, this one. And here we can write for this part, let me use maybe another color that will help you to understand. Here I am going to write this part as the character of this representation is obviously unchanged. This symmetry operation, character of this symmetry operation in the ith irreducible representation. And what about the next one? So this is also same, right? This is the character of the same operation in the ith, right? So this is also going to be chi I r, right? And what these are equals to, the right hand side? The right hand side is nothing but, if you see h by li. Now what is delta m dash? So when your dimensionality li is 1, so then it is one dimensional. When li is 2, then your representation, irreducible representation, is two dimensional, right? Now if you think of a one dimensional representation, then it is having a one matrix element, right? So, or what is the order of this 1D representation? That is 1, right? And what will be the order of a two-dimensional matrix? That is 2. right? 1 plus 1. So actually this is also what I'm trying to say. This is your dimensionality of your ith irreducible representation. The delta sum over m dash over delta m dash. So if there is only one element, that is your diagonal element is 1, means this could be either 1, this could be 1 or 0. So the only diagonal elements is going to be 1. Else then off diagonal elements are 0, right? So sum over the diagonal elements is going to be your dimensionality. So your Li got cut and you are left with your working rule that we are using, that character of R square of this from the same irreducible representation is going to give you the order of your point group. So this is proof of one of the working rule. What about the orthogonality rule? In that case, instead, so suppose you still have delta ij here. So if your irreducible representations are different, so from different characters, then the right hand side is going to be 0. So that is what your fourth, that is what your this last working rule is, right? So your right hand side is going to be 0 because your delta ij is going to be 0 because I not equals to j. Okay, so I'm not going to prove that, but I hope you can understand what I'm trying, what we have done till now, right? Now let me at least discuss some character tables, and based on that we will discuss what could be the Mulliken symbols and all. But let us first uh, get some uh, character tables. I will so draw. So we have in our disposal C2V point group, right? So how to write a character table? So on this axis we will write what is the point group here, and then we will write down the classes, like this is identity, symmetry operation, E, and then C2, right? And then sigma V xz along one plane and sigma V dash yz. Why you have written down two different way? Because these are belongs to two different classes. Okay, now from the great orthogonality theorem we know the number of irreducible representation is going to be same as the number of classes. Then we can expect there are four uh, irreducible representation, right? Okay, what will be them? So we know already that there would be one totally symmetric one. So let me write that thing first. So this is a totally symmetric representation, right? Then we are going to use the working rules that we have in our hand, that one is sum over I Li is going to be Li square is going to be H, right? So Li is the dimensionality, and for C2V what is going to be, suppose let me write it as this is going to be chi 1 chi 2e chi 3e character of fourth of e. What I'm trying to say is this is 1 square plus chi 2 e square plus chi3 e square plus chi4 e square is going to be how many? What is the order of this point group? That is 4, right? So this is going to be 4. Now we know that dimensionality can't be 0, right? So if it can't be 0, and means the character of the identity is also not going to be 0, right? It could be minimum 1 and then more than 1 depending on the dimensionality, right? So we know that it can't be 0 and could be 1 or 2, but accordingly this equation, what we can understand, these all are going to be 1, right? Else it is not possible, else 1 have to be 0 or something like that. So I will erase this thing and I will write all the values as 1, and from there we can come to an important conclusion that all the irreducible representation of C2V are one dimensional in nature. Okay. Now we can use another working rule into the work, that is our orthogonality principle, right? Sum over I chi I r chi j r will give you 0, right? So if I write it as chi 2 C2 chi 2 xz, actually sigma v xz, then chi 3, actually chi 2 sigma v dash yz, right? So if I do that here, I am going to get first, for the first one I am going to get 1 into 1, then the second one I am going to get chi 2 C2, then I am going to get chi 2 sigma v, and then I am going to get chi 2 sigma v dash is going to be 0. And I am now, as I know, these are all one dimensional irreducible representation, there will be no, so I will just also write whatever we are going to, all the irreducible representation of C2V are one dimensional. So characters of asymmetry operations could either be 1 or -1. This is known. So from that we can see that it will give me all 1, but so what I'm trying to say, if we have to use the orthogonality principle, we can see all will be 1, and in each of the last 3 representation, 2 of the 4 are going to be minus. So let me take this one minus first, this, and then this, and then this. So this is a character table of a C2V matrix, obviously. Now if you see what else is there in a character table, there will be these basis sets, right? What we have already discussed. So first, the if we remember that what belongs to xyz, actually you will see z was your uh, totally symmetric one, and x belongs to gamma 3 and y belongs to gamma 4. And for the quadratic functions like z square or x square and y square, if you multiply the characters with itself x square, you are going to see they are going to be totally symmetric. So actually this z will be z square, x square, y square and all. If you multiply these two, the characters between each, you will see your xy is actually going to be gamma 2. It will have a symmetry species along this gamma 2 irreducible representation. Now obviously xz and yz will lie on this particular, it will have this particular symmetry species. So this collection of these characters is actually called the character table. Characters is character table. And okay, now if I have to go to the Mulliken nomenclature, then we all know that if for a one-dimensional, so how to do Mulliken nomenclature? Mulliken nomenclature. If one-dimensional IIRs, irreducible representations, then it could be start with A or B. Which one will be A, which one will be B? If it is symmetric with respect to the most prominent symmetry operation, that is here C2, then it will be A, else it will be B. So see, along C2 the symmetrics are gamma 1, gamma 2, antisymmetric are gamma 3, gamma 4. So these will be known as A and these will be called as B. Now what could be the other nomenclature to differentiate between the irreducible representations? It will be some other things, right? So we have to look at the next possible symmetry operation now, which is sigma v, right? So we'll name it 1 or 2 depending on if it is symmetric with respect to the sigma v, then it would be 1. It would be, if it is antisymmetric with respect to sigma v, then it would be 2. So then we'll write it a1, a2, b1, b2. There are also other nomenclature also. If your character of your sigma h or molecular plane is going to be symmetric 1, then it would have a single dash, suppose x single dash. If it is -1 antisymmetric, then it would have x double dash. If your character of the symmetry operation of inversion is symmetric 1, then there would be a subscript, that is Gerard G. If it is antisymmetric with respect to your point of inversion or symmetry operation I, it would call a subscript Ungerard will come like this. Okay, so we can before going there, let me have some more blank sheet maybe. I will have some more blank sheet to discuss actually before going to solve the assignments. Okay. So um, what I was telling that um, let us also discuss the C3b point group. For C3b point group, what are the symmetry operations? Obviously, identity is there, E, and then there is C3 rotation. Obviously, there is another rotation, that is C3-2 or C3 inverse, which actually have equivalent uh, equivalency. That's why they belong to the same class. So we can write it as 2C3. So there are two kind of operation of similar kinds. So this is actually, you can write it 2C3. And similarly, C3b point group example is ammonia. So there are three vertical rotation reflection planes are there, which are also equivalent, unlike the reflection planes of C2v. So these 3 sigma v are actually equivalent. So actually the number of order or number of total operation in C3v is 6 and number of class is actually 3. Okay. So as number of class is 3, then from the GOT or working rule we know there is going to be 3 irreducible representation. Okay. Now obviously the first one is going to be totally symmetric. What about the others? So obviously we have to look at the working rule, that is sum over I dimensionality square is going to be h. Here it is 6. So we already have 1 square. Then we are going to have, right, chi of character of E in second irreducible representation, character of E in third irreducible representation, which is going to be chi 2v square plus chi 3 square is going to be 6. So as you can see from here, the only possibilities are 1 and 2, right? And dimension can never be negative. That's why it could be either 1 or 2. So I will write the values. It could be either 1 and 2. 1 square plus 1 square plus 2 square is going to give you 6, right? So as you can see, there are two 1D irreducible representation and one two-dimensional irreducible representation in C3v point group. How to get the other two? Obviously, another working rule is there, the orthogonality principle, right? That sum over I, character of ith operation, that is of, sorry, ith irreducible representation of R symmetry operation multiply by the character of symmetry, same symmetry operation from a different irreducible representation is going to give you 0, right? So let me write here chi 2 C3 chi 2 sigma v. What about this? Chi 3 C3 chi 3 sigma v. One important thing to discuss here, unlike the C2b point group, here as I earlier mentioned, that actually there is two operations are written such a way that you may think or you may get confused that this is the only one symmetry operation is there. Actually 2C3, actually there are two symmetry operations are there. In case of 3 sigma v, there are 3 sigma v operations are there. So while writing this, what I am trying to say, that first is 1 into 1, then actually it is 1 into chi 2 C3, and if I break the thing, it is actually chi 2 of C3 2 is also there. Okay, what I am trying to say. And also obviously there is 1 into chi 2 of sigma v of one kind, 1 into chi 2 of sigma v of another kind, but belongs to the same symmetry operations and hence have same character values. So I am writing this like this for the just for one time for your sake. So I will just write it again. So it will be 1 into 1. Actually this means 2 into chi 2 of C3. You have to keep this thing in mind that whenever what are the number of uh, what is the number of similar operations are there, so that you need to calculate here, else you are going to get a wrong value. So instead of these three as the character value, character is going to same for all these equivalent operation, that's why I am going to multiply with 3. Character of this chi2 c3 and character of chi2 c32 actually is going to same, that is why I am multiplying by 2. So that's what I am doing here. Chi2 sigma v, just I am writing it will be 0. So as it is one dimensional, so 1 will be 1. This is going to be 1 plus 2 chi2 c3 plus 3 chi2 sigma b, right? So the only possible values could be for chi2 and chi2 sigma v is going to be 1 or minus 1, right? Because they are because of the orthonormality principle, right? And they belongs to one dimensional representation. So actually it will be 1 and minus 1 here. I'll just write it here, 1 and minus 1. If it was minus 1, then see, this is minus 1 and this is 1, then this equation is not valid. 1 minus 2 plus 3. So that is going to give you plus 2, not 0. The equation is possible only when chi2 is 1 and chi3 is minus 1. Then this orthonormality principle takes place, and that is why I have written it like this. So what are the Mulliken symbols till now? This is A. This is also going to be A, but this is A1, this is A2. What about this? So for a 2D irreducible representation, we denote it by E, and let us see what is going to be chi3 and chi3 sigma v. So again we are going to use the this orthogonality principle, and we will multiply gamma 1 with gamma 3 and gamma 2 with gamma 3 to generate two equations, because as it is no longer a one dimensional irreducible representation, we don't know if it is. So when it was one dimensional, we know either one is going to be 1 and another going to be minus 1. But when it is a two-dimensional irreducible representation, we don't know the exact character values. So we need two equations to get two values, right? So we will do that when we multiply gamma 1 with gamma 3, we are going to generate 2 plus, so what we are doing, 1 into 2, 2, 1 into chi3, and there are two similar kind of C3 is there, so 2 into 1 into chi3 of C3 plus 3 into 1 into chi3 of sigma v is going to be 0. So this is leading to 2 plus 2 chi3 of C3 plus 3 chi 3 of sigma v is 0. What about another equation? Gamma 2 into gamma 3. Here we will get 2 plus 2 chi 3 of C3 minus 3 chi 3 sigma v, that is 0. Now, as you can see, irrespective of the value of chi 3, they are going to give me 0. So actually chi 3 is actually 0. Okay, chi 3 sigma v is 0. Chi 3 sigma v is 0. And what about chi 3 of C3? If it is 0, then 2 plus 2 into C3 is going to be 0, then chi 3 of C3 is going to be minus 1. So we'll just put the values here. Minus 1 and 0. Here comes one of the very important question, that what is the meaning of this minus 1 and 0? Does this 0 means that 0 means we know annihilation, right? But for a two-dimensional irreducible representation, does it mean the same? Does it mean when you are going to operate sigma v on your basis set, you are going to get an annihilation of you are going to annihilate your uh, function? No. If you are going to annihilate, then how can it be a symmetry operation? It can't be, right? So actually what it does mean, and Professor Datta has very means logically he gave you that means the understanding was very logical, because uh, there could be two possible uh, reasoning behind this character of 0. Either that the basis which they are going to use, they are going to interchange the position, or one is going to change the one is going to change and another going to remain unchanged. What I am trying to say, so as this is a two-dimensional uh, irreducible representation, then let me take the basis set as x and y. Suppose they are changing together, right? That's why you are going to get a two-dimensional uh, irreducible representation, right? So suppose uh, we are talking about sigma v, right? So suppose uh, what I am trying to say, if they are going to interchange the position, that is x becoming y and y becoming x, then what could be the possible transformational matrix here? 0 1 1 0, right? This is one kind of sigma v could be, right? What could be the another type, another transformational matrix? What I was trying to say, one is going to be same and another's changing its sign. So it could be 1 0 0 minus 1. Then see, the character of this transformational matrix is 0, but it does not annihilate your uh, function. Okay, that is what happens. So in the two-dimensional IRs, so you need to be very careful what this character actually means. So this is one of the important lesson what we can take away from this kind of examples. So the other thing what I am going to discuss, before discussing that, let us solve the uh, uh, weekly assignment problems from assignment 6 and 7. So the first question is, for a D2H molecule, consider the principal axis to be along z direction using the unit vectors along these three Cartesian axes as basis. So your unit vectors are x, y, z, right? So this is your basis is already given, Cartesian axis as basis. The resultant symmetry operation for sigma xy and c2x, what they are going to be. So sigma xy and c2x. I am not going to think about the D2H molecule for now, because remember, whenever you are going to see that there is a C2 symmetry, and C2 being the principal rotational axis, then remember always that there is not going to be any interchange of the bases. Only there is going to be either they are going to change their values, but they are never going to interchange. So you can directly do it when you, this is your basis set. First, when you are applying c to x, so your x along x is not going to change, but y and z are going to change from y to minus y and z to minus z, right? So I'll write this. I have not applied sigma xy yet, but when I apply c to x, it will become x going to remain x and y going to minus y and z is going to be minus z. Now when I am going to apply the reflection along xy plane, then my x and y are going to be remain unchanged, x and minus y, and z is going to change. So what I am ultimately getting from starting, what is the equivalent symmetry operation of this that can lead to x minus y z, and that is, if you see, your x and z are remain unchanged, and as your y is getting changed, so this is a reflection along x z. So your fourth option is going to be the right option. Okay. Now the second question. So they have given that consider a carbonate ion depicted in the following figure. The three oxygen atoms are designated as 1, 2, and 3, and the carbon atom is designated as 4. Okay, so this is your carbon, this is your oxygen 1, this is oxygen 2, and this is oxygen 3, and this is x-axis, y-axis, and z-axis. Okay, now taking the pz orbitals, the three oxygen atom as basis, that now your basis function is pz orbitals of these oxygens, each oxygens, pz1, pz2, pz3. The transformational matrix is given, represent which symmetry operation. So let me use this transformational matrix to work on my basis set, and let me check what is my ultimately what I am trying to get. pz1, it is working on pz1, pz2, pz3. So if I do the matrix multiplication, what I am going to get? So it is a 3 into 3 matrix multiplied by 3 into 1. So sorry, so 1 into 3, right? So actually I am going to get if, did I say the correct thing? Yes, this is 1 into 3. So that is why I am going to get 3 into 1 matrix as a product. What I am going to get? I am going to get for the first one, it has interchanged. pz2, pz1 has become pz2, pz2 has become pz1, and pz3 remain unchanged, which actually means your 2 has gone to 1 and 1 has gone to 2, but 3 remains unchanged, which actually means that it is an plane along YZ. So that is why it is along, so I should not draw it like that. It is actually misleading. I will draw it like this. It will go, it will intersect 2, 4, 1. This angle it will intersect, it will be along YZ, right? And it will go inside the carbon and the third oxygen. So their position will be remain unchanged. So your third pz orbital is remain unchanged, but your position of the pz1 become pz2 and pz2 become pz1. That is why this is an sigma v plane. So this is they represent this symmetry operation. Okay, I hope that is clear. Now I will go to next question. So the next question is the result of the product between C2X and C2Y. Okay, C2X and C2Y. Suppose I am working on XYZ again. So what will happen? First, I will work on C2Y and it will become minus X, Y remains same, Z remain unchanged. Now when C2 will work on this X, so X will remain unchanged, minus Y and Z. So what could be the ideal symmetry operation of this actual result of this product? So this could be C2Z, right? Where your Z will remain unchanged and XY is going to change their position. So it is C2Z would be a correct answer. Now question number 4, a group of order equals to 4 is necessarily cyclic, is necessarily acyclic, can be either cyclic or acyclic, is always commutative. Actually, this question, to be honest, is not a good question because the cyclic group and acyclic group, they don't have a definition in the case of the order of the group. What I remember, so actually the answer of this I have also checked from the assignment. Actually, the answer was can be either as cyclic or acyclic. Actually, cyclic means only one axis of rotation is going to be there. Okay, and there will be no other symmetry elements. Obviously, E is going to be there, but there is no other symmetry operation other than that E and C2, and maybe Cn, right? So that doesn't really give you an idea that a group of order of 4 is going to be what, right? So we're not going to discuss that question further, but let us go to question number 5. It is actually from question number 5 is from the Raman scattering. So why are the laser sources ideal for the excitation in the experiments dealing with Raman scattering? Actually, this has given also as a MCQ question, but it should have been a multiple correct answer. The two possible correct answer is one, obviously the monochromaticity of the light, and another being the high intensity. As you remember that for Raman scattering, we are going to deal with induced dipoles with the oscillating electric field, and induced dipole and oscillating your electric field, when only your electric field is very high, then only your induced dipole, that interaction is going to be high. Okay, so your laser should have, why your laser used, one, obviously the monochromaticity, then only you are going to see very specific Raman peaks, else your Raman peak will be there would be too many Raman's peak, and it would not be an ideal scenario, and obviously you will also need high intensity laser source. The next question is 6. The combination which has or have a group and its subgroup is R. To be honest, you have to have an idea of point groups here for this question. Actually, the correct answer are the first and the second, and first, third and the second. For that, you try to look at the uh, definition. First, look at the definition of group and then subgroup. Actually, you will see your C3b is actually going to be a part of your octahedral, and for that I will suggest you to go to online website like jacobsymmetry.jacobs.com, and there you will get to see the character table, and you can even visualize your molecules in that different symmetry elements. For question number 7, the cyclic group among the following is, obviously for a cyclic group there is only going to be one rotational axis, that is C3. When Cn here, it is going to be C3. The first option is going to be correct. So with that, we are going to discuss week 7 assignment also, because we have discussed the material. So let us discuss that also. So for week 7 assignment, the sum of the square of the dimension of all irreducible representation in a group is equals to, so this actually tells us from the working rule, right? So sum of square of dimensions means Li square of all the irreducible representation is going to be equals to H, right? So its order. So this is going to be the correct answer. Now the next question, the point group of ClF2 molecule and its corresponding number of irreducible representations are respectively what? So ClF2 molecule, how it will look like? Chlorine, fluorine, like this. So this is actually a pyramidal, trigonal pyramidal structure where there are two lone pairs are also that we need to take care of. So if you see this, then this has a point group of C2V. Why? So it has a, if I take other color, then you will see it has a C2 axis of symmetry C2Z along this, and there are two um, vertical reflection plane which contain C2Z, right? One along the molecular plane dissecting the lone pairs, right? Another along the FCl bond. Okay, so there are two, obviously there is E, C2Z, two kind of C2V. So this is an C2V point group, and obviously for a C2V point group, the number of irreducible representation is going to be 4, right? So the first option is correct, the second option is correct. Now question number 3, matrix elements behaves like a set of orthonormal vectors for what? Matrix element behave like a orthonormal set for vectors for reducible but not irreducible representation, irreducible but not reducible representation, reducible as well as irreducible representation, and one dimensional irreducible representation. From a whatever idea we have of great orthogonality theorem, one of us will tick that it is true for irreducible but not for reducible representation. But that is not correct. It is going to be actually correct for both reducible and irreducible representation. If you have a irreducible representation and a reducible representation, try to do that for a that orthogonality theorem or that whatever working rule we have, you are going to see that that is actually going to work even for reducible or irreducible representations. Okay. Now question number 4. For the irreducible representation, one irreducible representation is given. What is the Mulliken nomenclature? Obviously, from the character of identity, we can understand that it has a dimensionality of 1. Then obviously it could be either A or B. And as we can see, the principal rotational axis is C3. Along these, this is symmetric. So it will be A. So we'll start with A. So there are two possibilities, A1G or A2. So B1 and B2 are excluded. So there are two possibilities now, A1G and A2. Now looking at the character of the for the symmetry operation of center of inversion, it is symmetric. So it will be A1G. So A1G is the correct answer. Okay. Now question number 5. A two-dimensional representation may have the characters with the value. So as we already know for C3b, right, it could have a value of -1 and 0. It will not have a value of 1, and W is actually a if you think this is actually a imaginary term is going to come, so it's not going to be there. So what about question number 6? For a irreducible representation, irreducible representation is given, so we need to get the Mulliken nomenclature for this. So what is there? So it is a two-dimensional irreducible representation. Obviously it is going to be E. Now um, based on the antisymmetric nature of the character for the principal axis of rotation, we can say this is going to be A2. Sorry, this is going to be B. Okay, first is going to be B. Hey, I am very sorry. I am very sorry. First, it's not going to be B because it is a 2D irreducible representation where it is E. Okay. Now, after that, uh, with respect to sigma h, this is uh, symmetric. So, but we can't say it is symmetric like the case for um, actually we can say that E1 dash, it is symmetric. Um, for a two-dimensional case, what could be the answer? I am also getting confused because it can't be 1 and 2 based on that C3, right? Because it is already E based on the 2D. Now 1 and 2 would be depending on, this is not really a symmetric antisymmetric question. So the probable answer is going to be E1 dash. To be honest, I'm not sure. Please check the correct answer for this. Why I have ticked this question? Because it is symmetric, looks like it is symmetric with respect to the molecular plane, and there is only one option where there is only one dash is there. That's why I have marked that as a correct answer. Okay, with that, actually I have another kind of questions, but do we have some time? Yes, we do have some time. So within this speculated time, I would like to show you that how to. So this is going to be important for the next few lectures. So that this was not done in uh, 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 the lecture series by Datta sir. So I am going to show you this so that you can use this principle or know how to do this and solve um, or break down the reducible representations into irreducible representations. Okay. So now again we know I will again write the orthogonality, the great orthogonality principle here R gamma I R mn multiplied by gamma j m dash n dash of this going to be h divided by li lj delta m dash delta n dash I. From here, we are going to, we already know we are going to get two working rules, right? One is R chi IR. If the we are getting the character from the for the symmetry operation from a same irreducible representation, take a square of that, we are going to get the order of the point group. And another is, so I will not write it like this. One and two is same thing, but characters for different irreducible representation is going to give me 0. Now what I know that my reducible representation, I can write it in a linear combination of my irreducible representation, right? So I can write it like this. Suppose Aj is the number of irreducible representation and gamma j, right? So this is the jth uh, irreducible representation and it is there a jth time and we are summing over j, right? This is an easy way to describe what a reducible representation is. What another thing we will require here, a character of a symmetry operation. Okay, this is what the character of this reducible representation, actually what I'm trying to say, the character of this reducible representation, then accordingly this is going to be jth aj chi j of r, right? If I can write it my reducible representation like this, then one of the characters, suppose I am now taking one operation of that reducible representation, then I can write that my character of a reducible representation of a character of operation from a reducible representation is going to be the sum of the character of the representation and multiplied by their how many times that is there, right? I can, from here I can write this. So these are basically, this is a result of this statement. Okay. Now I am going to multiply this, what I am trying to get, show you what I'm trying to say. If I now multiply one of the character of a irreducible representation with this character of this a reducible representation, and then sum over R. Okay. So what we are doing here, so let me rewrite this once again in here. We are multiplying the character of this reducible representation with a character of the same operation from a irreducible representation for summing over all the R. Means this is for one irreducible representation. What we are going to expect, summing over all R. What is chi R? Chi, this we know, that is, we have defined it, J A J chi J R multiplied by chi I R, right? Now if I ex, ex means expand this for all the j, what I am going to get, suppose for all R, suppose I am j from 1 to n, suppose I am going to write a1, then it is chi1 R, obviously this is I, so as we are the sum over j, right, not R, plus a2 chi2 R, this way we can go somewhere, and obviously I is a part of j, so at some point it will be aj, sorry, ai chi I R, and obviously it is multiplied by chi I R, and again it will go on, right? And this is what this is going to give me. See, we have already defined from the orthogonality principle, when it is going to multiply sum over R I1 when I not equals to a, when my I not equals to j, that time this part is going to be 0, so this is 0, this is 0, whatever term is there is 0. What about this? Here I equals to j, right? So this is going to give me this, actually chi I R square, so this is going to give me ai h, right? And what about the other terms? These are going to also be 0. So actually what we ultimately got is sum over R chi of character of the reducible representation multiplied by chi of I of R is going to be ai into h, and ai is in other terms we can write AI is 1 over H sum over R chi R chi 1 R. This AI is the number of times the ith irreducible representation occurs in the reducible representation. I hope you get the idea how if you have, so we had started with two questions, right? See, we had started with two questions, that how would we know the exact number of irreducible representation for a particular point group. So from great orthogonality theorem, we already know that the number of classes possible is going to be the maximum number of the irreducible representation. And then we also get to know which representation is reducible and which one is irreducible. So actually your reducible can be broken down into your irreducible representation when you do this kind of uh, this kind of thing. If it can't be broken down, so if uh, you are going to get your gamma r is going to be only gamma 1 one time, then it is unreducible. If it can't be broken down into any further irreducible representation, lesser dimensionality like that, so then it is irreducible. So you can, so we got the answer for both the question what we have started with, the class we have started with. So for clarity, what we will do, we will solve only one question. I have it here, and we can start the next class from here. That deconvolute the following reducible representation into the irreducible ones. Represent reducible representation as gamma as sum of irreducible one. So for the first case, actually, let us solve at least one to get the idea of whatever we have discussed till now. So your reducible representation is given for a particular point group. I have provided the character table of the point group here, and we need to find out that what are the constituting irreducible representation behind this particular reducible representation. Okay, so let us start for the first one, the for the D2 at least. So I will just write D2 E. So I will not write this. This is a waste of time. I'll just write it here. So your gamma reducible is 4000 What we already know the formula, that is your AI is going to be 1 over H sum over R, character of your reducible representation multiplied by character of your ith irreducible representation of the operation, same operation. Okay, so for this one, for D2, let us see how many times this A irreducible representation is there. Okay, that will be 1 over the total. So how many total operation is there? So H is 4 for D2, so 1 by 4. Then sum what this we will do, that is 1 into plus 1 into 4. Okay, and what about the others? We will do the character of C2 in the reducible is 0. 0 into plus 1 plus 0 into 1 plus 0 into 1. This is leading to be 1. What about A of B1? Similarly, we will able to show this is 1 into 4 into then 0 into 1 then plus 0 into 1 plus 0 into 1, which will lead to 1, then A B2 1 by 4 1 into 4 plus 0. And similarly, because the character of the reproducible representation is 0, that's why it become a little easy, because it is all going to be 0 and except the first one. So similarly for B3 you will also be able to see it is going to come as 1. So what we get is that your this gamma R for D2 is actually is carrying all the irreducible representation one each one time. Okay, gamma R is equal to A1 plus A plus B1 plus B2 plus B3. Try to solve for the rest of this. So the rest of this B, C and D will start from the next class from here maybe. And as the time is already over, so let us stop it here. I hope the session was useful uh, for solving the next set of assignment maybe, or uh, understanding the week 8 and week 9 uh, um, whatever lectures are going to come, mainly based on the vibrations of polyatomic molecules, the normal mode of vibration. These all are going to be based on these uh, reducible, how you break down the reducible into the irreducible representation and all. It will be based on those. So I will urge you to solve these uh, questions, whatever there. So this note will be shared to you in the Swayam portal. So please try to find out this question and try to solve it by yourself, so that in the upcoming lectures you will find it easy in the lecture notes. So with that, let us end today's session, and I thank you for joining. And with that, I'm stop presenting my screen. So okay, we'll meet you on the next session. Thank you for joining.